Hello there, and welcome to the Whispering Science. Tonight we drift softly into one of the most mysterious intersections in all of human knowledge, the place where your mind, that quietly active inner world, just might be connected to the deepest layers of the universe itself. This is the enigma of quantum consciousness, a subject so quietly astounding that even some of the world's greatest minds have spent sleepless nights pondering its possibilities. Now, I do hope this isn't too interesting that it keeps you awake, but if it does, well, at least you'll have learned something fascinating about the idea that your conscious experience, your thoughts, dreams, and sense of being could possibly be shaped by physical phenomena at the tiniest, most fundamental level of reality. Before we begin, if you enjoy these slow science journeys, I'd be ever so grateful if you tapped the like button, subscribed, or even just left a comment telling me where in the world you're watching from and what time it is in your corner of the night. One of the joys of science is connecting across space and time, much in the spirit of this topic. So, settle in, get comfortable, and let's begin our quiet voyage into quantum consciousness theory. Is your brain connected to the universe? The notion that there may be a link, a bridge between the inner space of consciousness and the outer universe of quantum physics, is not just a product of poetic speculation, but the meeting point of two of humanity's grandest scientific mysteries. On one hand, the mind, where it comes from, what exactly it is, and how subjective experience emerges from grey matter. On the other, the quantum world, that realm too small to see, yet ruling the very behavior of atoms and energy, where particles can be in many places at once, where outcomes are fundamentally uncertain until they're observed. In recent decades, a handful of researchers and philosophers have begun to ask, softly but insistently, whether perhaps these two mysteries are not wholly separate. Might it be, they wonder, that understanding one could shed light on the other? The theory of quantum consciousness suggests just that, offering an idea that is bold, controversial, and at first blush almost impossible to believe. In the story ahead, we'll gently explore what quantum consciousness really means, why it matters, what makes it such an alluring, if polarizing idea, and whether there's any solid science to support it. We'll trace the thoughts of pioneering physicists and neuroscientists, look at the remarkable behaviors of quantum particles, and peek inside your own brain's hidden architecture. All the while, we'll place each idea in context, never getting ahead of the evidence, and never letting imagination substitute for truth. As we journey, you might find yourself surprised by the genuine scientific mysteries still left to unravel, and perhaps by the curious connections between your midnight thoughts and the fabric of the cosmos itself. What is quantum consciousness exactly? To answer that, let's gently draw back the curtain on two vast realms. One is the world of your mind and feelings, and the other is the mysterious landscape that quantum physicists investigate deep inside atoms. Quantum consciousness theory proposes that these two realms are, in some fundamental way, intertwined. Not just that your mind arises from the electrochemical activity of billions of neurons firing chemical signals, a view well supported by classical neuroscience, but that perhaps something further and stranger occurs. That quantum phenomena, like superposition and entanglement, play a crucial role in allowing consciousness to exist at all. In the boldest telling, quantum consciousness suggests that the processes inside your brain may not be solely the result of classical macroscopic biology, but could rely on the delicate, almost paradoxical behaviors at the quantum scale. But what does this really mean? Imagine for a moment that your thoughts, awareness, even your sense of I am, exist not just because neural networks pass signals in deterministic or even random patterns, but because at the tiniest possible scale, your brain's molecules are dancing to the tune of quantum mechanics, the theory that governs the behavior of the universe's tiniest building blocks. According to the most enthusiastic proponents of quantum consciousness, this could explain how the brain creates a unified, self-aware mind from billions of separate firing neurons. It might answer why the subjective inner world feels so radically unlike anything else we experience in science. In quantum physics, after all, particles can be in multiple states at once, only choosing a definite state during the act of measurement. Some theorists have wondered, Could your conscious experience, which somehow collapses a multitude of sensations, memories, and thoughts into the single stream of awareness you actually feel, be borrowing this logic from quantum mechanics? It's an idea that blurs boundaries, both between disciplines and between you and the world that surrounds you. And while to many it sounds fanciful, even magical, there are rigorous thinkers and experimentalists who take it seriously enough to study, argue, and attempt to test it scientifically. Still, quantum consciousness is not simply an alternative account of the brain. It's a hypothesis suggesting that the key to understanding the very existence of consciousness lies in accepting quantum reality with all its strangeness as part of the brain's functioning. Now, it's important to say that quantum consciousness is not one single tidy theory, but an umbrella for a wide variety of related ideas, each grappling with the same haunting question: how does subjective experience, your unique inner sense of being, emerge from physical matter? Some theorists suggest that consciousness is a fundamental property of the universe, just like space, time, and mass. Others argue it emerges specifically because of certain kinds of quantum processes happening, possibly in the microtubules of brain cells. Still others are skeptical that quantum effects are necessary at all. What unites these perspectives is the sense that simply treating the brain as a traditional biological computer running on chemistry and electricity alone cannot explain the specialness of mind. Crucially, quantum consciousness also attempts to reach across a chasm faced by all the sciences known as the hard problem of consciousness. That all of our detailed physical descriptions of the brain's mechanisms can tell us what the brain is doing, but cannot explain why those mechanisms give rise to the vivid, personal sense of awareness we feel each moment. The hard problem, a term made famous by philosopher David Chalmers, asks, why should certain brain processes be accompanied by inner experiences at all? Why is there a you inside your head and not just a smart but empty processing machine? Quantum consciousness theorists propose that perhaps only the strange features of quantum reality, its inherent unpredictability, interconnectedness, and ability to link faraway objects instantly, are up to the task. The argument, while highly controversial, has a kind of poetic audacity to it. By proposing that your mind might be fundamentally quantum, the theory invites us to see consciousness as something that is woven into the fabric of the universe itself, not merely a byproduct of neurons, but a process or entity lifted straight from the same rulebook that allowed stars, galaxies, and perhaps even life to emerge from chaos. It is a perspective that both inspires and troubles neuroscientists and physicists alike, precisely because it stretches so many comfortable assumptions. Yet for all its controversy, quantum consciousness is not simply philosophical hand-waving. There are testable claims, detailed arguments, and most importantly, a growing, if still hotly debated, body of research investigating whether real, measurable quantum effects might actually occur inside the warm, wet, chaotic environment of the living brain. As we continue our journey tonight, we'll look carefully at what is actually meant by classical versus quantum explanations of the brain, what quantum physics brings to our understanding of the universe, and how these radical theories might, just possibly, change our understanding of what it means to be human. But for now, simply let the idea settle that behind your thoughts and sensations there may exist threads connecting you, quite literally, with the most fundamental truths of the cosmos. To truly appreciate the quantum consciousness hypothesis, it helps to gently trace your awareness back through what neuroscientists have uncovered about how the brain operates at the level they can observe and measure. Classical neuroscience, meaning the study of the brain's workings with well-established physical, chemical, and biological principles, has, over the last century, built a wonderfully intricate model for understanding how thoughts, emotions, and memories arise in the living brain. Imagine, softly, the roughly 3 pounds of tissue nestled inside your skull, containing around 86 billion neurons. Each neuron, though tiny, resembles a complex branching tree, extending filaments to reach out and touch thousands of neighbors, sometimes connecting with up to 10,000 other cells. Information in the brain travels through these slender branches, called axons and dendrites, as a pulse of electrical activity, an action potential, much like a gentle wave propagating down a wire. When this electrical signal reaches the end of the axon, it arrives at a junction called a synapse, where it cannot cross directly. Instead, the neuron releases a carefully selected molecule, what we call a neurotransmitter, into the minuscule gap. The receiving cell absorbs these chemicals, and if the message is strong enough, generates a new electrical impulse, continuing the cascade. All of your hopes, dreams, perceptions, and even your ability to unwind at the end of a long day are supported by these cycles, electrical, chemical, and remarkably reliable patterns sweeping through your neural circuitry. You can think of your brain as a teeming city, alive at every moment with the buzz of micromessages, each neuron acting as both a citizen and a city block. From a classical point of view, consciousness is something that emerges from this sprawling electrical dance. Patterns of neuron firing traveling in coordinated rhythms, called brainwaves, give rise to different states of mind. The slow, dreamy oscillations of deep sleep, the faster pulses of alert attention, and countless variations in between. This approach to brain science was built on the careful work of countless researchers. At the end of the 19th century, Spanish scientist Santiago Ramón y Cajal, often called the father of neuroscience, painstakingly sketched the first images of neurons, revealing their distinct shapes and suggesting the importance of their connections. In the 1930s, Alan Hodgkin and Andrew Huxley mapped the precise movements of ions across the neuron's membrane, laying the mathematical foundations for the action potential. And by the second half of the 20th century, pioneers like Donald Hebb and Eric Kandel explored how connections between neurons could strengthen or weaken with experience, showing how learning and memory might be encoded. Fascinatingly, there is a scale to this complexity. The cortex alone, your brain's wrinkled outermost layer, holds as many connections as there are stars in our galaxy. In total, estimates suggest there are more than 100 trillion synapses inside your head, each one flickering on and off throughout your day and night. These numbers are almost unimaginably large. Your brain is the most complex known object in the universe. And yet, under the hood, the models classical neuroscience has developed seem to do a remarkably good job predicting much of your daily experience. Electroencephalograms, the EEGs, can track your shifts between wake, dream, and deep sleep. Brain imaging like MRI and PET scans display networks lighting up as you read, remember, or relax. Yet, for all this intricate mapping, classical neuroscience comes up against a truly puzzling question. No matter how detailed the model, it describes the mechanisms of processing, how information is stored, relayed, and recalled, but it does not explain why there should be a subjective you, a stream of conscious experience inside your mind. This limitation is sometimes called the explanatory gap. We know, for instance, that certain brain injuries can rob a person of language, or memory, or even a sense of self. We can predict these breakdowns with fair precision, but we cannot say why the firing of neurons should give rise to the personal, first-person feeling of being you. Despite this mystery, the classical neuroscience framework remains extraordinarily useful for explaining sensory perception, movement, emotional experience, and much more. It models the mind as an emergent property, a kind of organized chaos, occurring whenever billions of fast, flexible cells interact in just the right way. This view is supported by breathtaking statistics. For example, your brain can make a decision in as little as 0.2 seconds, and, in that span, millions of neurons may participate in processing incoming stimuli, storing relevant memories, and guiding an action. But if you zoom in closer, much closer, beneath the cellular, molecular, and atomic scales, classical neuroscience yields to the world of quantum physics. Some theorists look at the brain's complexity and see not limits, but possibility. Perhaps in the shadows beneath this thunderous electrical activity, there are quantum effects quietly shaping the inner experience, effects classical biology cannot see or explain. As we hold this idea softly, it is important to recognize how successful the classical model has been. It provides the foundation of all our medical treatments, guides neurosurgery, and shapes the therapies for psychological illnesses. Nevertheless, the explanatory gap remains, a gentle puzzle that encourages brave thinkers to wonder, what, if anything, might be missing? With a calming breath, we remember, the journey into quantum consciousness is not a rejection of classical neuroscience, but an exploration into whether deeper layers of reality help close the gap between matter and mind. As we continue along this gentle journey, let's look closely at the realm where quantum consciousness claims its roots, the strange, elusive world known as quantum physics. This field is dedicated to studying the very small, particles and forces that operate at scales 1 billion times smaller than what your eyes will ever see, deep within the heart of atoms and molecules. Quantum physics first emerged in the early 20th century, when a series of puzzling experiments proved that the old, classical laws of physics, the ones that explain everything from falling apples to planetary motion, just couldn't account for what scientists saw at the subatomic level. In 1900, Max Planck introduced a revolutionary idea, proposing that energy comes in discrete packets, or quanta, rather than as smooth, continuous waves. Only 5 years later, Albert Einstein used this concept to explain the photoelectric effect, showing that light, too, could act like particles. These discoveries, along with the work of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, gave rise to quantum mechanics, a wholly new framework for understanding reality. So, what exactly makes quantum physics so extraordinary, and how does it differ from the everyday rules that govern baseballs, cars, or even your own body? The answer lies in a small set of behaviors that all seem at first to defy common sense. First, there's superposition. At the quantum level, particles don't have to choose a single state, such as being here or there. Instead, they can exist in multiple places or multiple states at once, like a coin spinning in the air, both heads and tails, until it comes down. Only when you measure or observe the particle does it collapse into one fixed outcome. This raises profound questions. Is reality itself undefined until it's observed? Could the act of looking literally create the world we see? Then, there's entanglement, perhaps the most mesmerizing idea of all. When two particles become entangled, their properties become so deeply linked that a change to one, even if separated by vast distances, instantly changes the other. It's as if, upon meeting, two tiny dancers learn the same choreography forever, no matter how far apart they travel. Albert Einstein famously called this spooky action at a distance, though later experiments would confirm entanglement over distances exceeding 1,200 kilometers. Today, entanglement is used in real-world technologies like quantum cryptography and quantum computing, where the behavior of one qubit can instantly shape another's state. Other hallmarks of quantum physics include tunneling, where particles pass through barriers they should never get across, and the uncertainty principle. The more precisely you know a particle's position, the less you can know about its momentum, and vice versa. This isn't just a limit of our measurement tools, it is a built-in feature of the universe at its most fundamental levels. To give a feeling of scale, remember that quantum effects usually appear at the level of electrons, protons, and other subatomic particles, distances measured in picometers or even smaller. Quantum physics has been spectacularly successful at describing the invisible world. It predicts the behavior of semiconductors, the heart of your cell phone and computer, as well as MRI machines that peer inside your brain, lasers, atomic clocks, and even the fundamental chemistry of life itself depend on quantum phenomena. Yet the strangeness remains. In a typical atom, an electron can be described by a probability cloud rather than a simple orbit. It exists in all allowed places until measured. When multiple particles act in concert, their quantum states become linked in mathematically complex ways, allowing future quantum computers to perform calculations far beyond the capacity of even the fastest supercomputers. Now, why would any of this matter when it comes to the brain? For decades, scientists assumed that quantum phenomena were simply too delicate, too fleeting to operate inside living tissue. The brain is a warm, wet, noisy environment. Signals are blaring. Molecules are constantly jostling about. Quantum states, so easily destroyed by disturbances, were thought unlikely to survive here for more than a fraction of a picosecond. But quantum consciousness theories argue, with varying degrees of evidence, that perhaps certain molecular structures or processes in the brain might exploit quantum effects long enough to play a role in perception, memory, and the binding of your conscious experience. If this were true, it would mean your mind is not just sculpted by electrical impulses and chemistry, but potentially by the richest, strangest physics available in nature. It would open a door to remarkable possibilities, that your awareness, your very act of experiencing the world, could be entangled in quantum states that link you to the universe at large. There is, of course, still much debate and much to discover. Yet as you drift quietly through these ideas, you can appreciate the boldness. Quantum consciousness seeks to unite the most complex thing we know, the human mind, with the most mysterious science we've ever uncovered. In this dance of the very small, quantum physics provides both the language and the rules for understanding a universe that is not always what it seems. Whether or not consciousness depends on quantum mechanics, you are, right now, composed of trillions upon trillions of quantum particles, each a tiny flicker in the great cosmic night, guided by laws stranger and more beautiful than any dream. Now let's allow our thoughts to softly approach one of science's greatest riddles, the mystery of consciousness itself. Even as classical neuroscience explains the transmission of electrical pulses and chemicals across billions of synapses, it leaves a quietly lingering question at the heart of every human experience. Why do these intricate physical processes give rise to the shimmering reality of awareness? Why should the mere processing of information lead to the vivid first-person perspective that you, and presumably every other conscious being, live inside from morning to night? Consciousness, on the surface, is an everyday certainty. When you open your eyes upon waking, feel a sudden rush of memory, or savor the taste of tea, you're experiencing the rich inner film of sensation and thought that defines sentience. Scientists call this phenomenal consciousness, the subjective texture of being, while access consciousness refers to the brain's ability to process and use information, even in ways you may not notice or remember. But for as long as we have explored ourselves and our place in the universe, thinkers and ordinary people alike have marveled at the seeming gap between the material and the mental. From a biological perspective, the brain is a tactile, observable machine. Doctors can map specific functions to precise regions, auditory centers, visual processing hubs, circuits for pain and pleasure, thanks to both imaging technology and careful case studies that span over 100 years. Yet, these maps never seem to answer the core of the mystery. Why is information, swirling in the brain's electrical storms, accompanied by an inner light, a conscious point of view? This dilemma was most crisply articulated in the 1990s by philosopher David Chalmers, who famously drew a line between the easy problems of consciousness, such as explaining perception, memory, or mental control, and the hard problem. Why is any of this accompanied by experience at all? Why does a symphony's chord cause goosebumps, or the memory of sunlight bring a momentary wash of joy? The hard problem still resists solution, even as neuroscience makes astonishing progress in mapping the correlates of consciousness, meaning the patterns of brain activity linked to being awake and aware versus asleep or anesthetized. A further layer of intrigue comes from the unity of consciousness. Despite your brain's modular structure, dozens of regions firing for vision, hearing, touch, language, and movement, you enjoy your life as a seamless whole. Sights, sounds, sensations, and inner thoughts all appear woven into a singular story, featuring you at its heart. This phenomenon, the binding problem, raises the perpetual question: how does a fragmented, modular brain generate a unified, continuous experience? Historical accounts remind us that this challenge is far from new. Philosophers from Descartes to William James pondered the mind-body problem, the seeming dual existence of consciousness and matter. Some proposed dualism, believing the mind is a non-physical essence, separate from the physical body. Others, such as materialist thinkers, argued that consciousness is just what the brain does, nothing more or less. Yet, frustration lingers because no biological finding has yet explained the actual spark of subjective sensation. Statistically, consciousness is rarer and more fragile than we might imagine. Most of the universe appears unconscious, vast clouds of gas, burning stars, swirling galaxies. Only as far as we can tell, on select planets with intricate biology, does awareness flicker into being. It's estimated that there are about 86 billion conscious human minds alive today, among untold numbers of other animals who may share shades of subjective experience. The puzzle grows more fascinating when considering altered states. General anesthesia, for example, can erase all trace of subjective awareness, even though the brain remains physically intact and active in some ways. Hallucinations, dreams, and psychedelic experiences further blur the lines, hinting at the extraordinary powers and vulnerabilities of conscious states. All of this is what drives many scientists, physicists, neuroscientists, and philosophers to wonder if a physical explanation for consciousness might lie beneath or beyond ordinary biology. Could there be some elusive mechanism, possibly quantum in nature, that bridges the gap between unconscious information processing and the flowing first-person experience we call mind? Quantum consciousness theorists suggest that perhaps quantum effects, known for their holistic behaviors and unpredictability, offer at least a candidate solution. After all, in quantum mechanics, the act of observation itself shapes the outcome, a peculiar resonance with the mystery of how awareness might arise. While there is disagreement, even passionate debate, about whether the quantum realm has anything to teach us about the mind, all agree that consciousness remains the deepest mystery in science today. For now, as you let your own awareness rest upon this puzzle, you can appreciate the way consciousness gently resists all simple explanation, a living question inviting us to look deeper, both into the fabric of the universe and into ourselves. We now wander through a gentle corridor of history, glimpsing the earliest origins of the quantum consciousness idea, where scientists, philosophers, and bold thinkers dared to trace mysterious threads, linking the physics of the infinitesimal with the warm, flickering experience of awareness. To understand where today's theories come from, it helps to recall how, almost as soon as quantum physics arrived in the early 20th century, its strange implications began to stir deep questions about observation, the role of mind, and the very nature of reality. Surprisingly, some of quantum mechanics' founding figures themselves wondered if the mind had some role to play in the unfolding story of the physical world. In the late 1920s and 1930s, physicists such as Niels Bohr and Werner Heisenberg debated the famous measurement problem, the puzzling fact that a quantum system seems to remain in an indefinite state until witnessed or measured. In one memorable phrase, Bohr said that the measurement is not completed until it is registered by a conscious observer. Though Bohr himself was careful and often ambiguous, this language quietly seeded the idea that perhaps consciousness was woven into the laws of quantum physics. A more direct proponent arrived in the 1930s with the mathematician John von Neumann. In his influential 1932 book, Mathematical Foundations of Quantum Mechanics, von Neumann pointed out that if you follow the chain of measurement, a detector recording photons, then a readout, then neurons firing in the observer's eye and brain, you still never reach a purely physical collapse of the quantum state until you reach the awareness of the observer. He suggested, though cautiously, that consciousness itself might play a special role in bringing the quantum world into the definite forms we experience. This idea, sometimes called the consciousness causes collapse interpretation, has endured as a source of fascination and debate for nearly a century. Decades later, the legendary physicist Eugene Wigner took these thoughts a step further. In the 1960s, he proposed that physics, in order to be complete, might need to include consciousness as a fundamental ingredient, asserting that the act of observation, intimately linked to conscious experience, was necessary for the collapse of the quantum wave function. Wigner's views represent an early attempt to bridge physics with the mystery of mind, though even he later modified his stance at times as new evidence and arguments emerged. Outside of physics, philosophers in both East and West have long speculated about a cosmic link between mind and universe. In the 1970s, the British physicist David Bohm inspired by both quantum theory and holistic philosophy, propose that the observable world is guided by a deeper implicate order, a level where mind and matter may be fundamentally inseparable, only appearing different from the limited perspective of our everyday senses. By the 1980s and 1990s, a new generation of thinkers began to formalize quantum consciousness theories, aiming to testable ideas rather than philosophical musings. The British mathematician and physicist Roger Penrose and the American anesthesiologist Stuart Hameroff became leading voices, arguing that quantum effects in neural microtubules could underlie consciousness, a theory we'll slip into deeper in a little while. Even as mainstream science remained skeptical, pop culture was quick to embrace and sometimes misinterpret these ideas. Novels and films began to play with the possibility that our minds could influence reality at a quantum level, blending legitimate scientific puzzles with more playful fiction. The spread of these ideas in media sometimes led to confusion or exaggeration, yet it also kept public curiosity alive and inspired new generations to study both consciousness and quantum physics. It's important to note that many, perhaps most, physicists do not believe consciousness is needed to resolve the quantum measurement problem. Alternative interpretations, like the many worlds hypothesis, first proposed by Hugh Everett in 1957, which claims all possible outcomes actually happen in branching universes, avoid invoking mind altogether. For these theorists, consciousness emerges much later as an aspect of complex systems such as brains, and not as a central actor in the cosmic drama. Nevertheless, the history of quantum consciousness is dotted with brilliant minds who were unafraid to ask audacious questions. Milestones include von Neumann's 1932 treatise, Wigner's writings in the 60s, Bohm's ongoing influence, and, in the 1990s, the formal grounding of consciousness quantum links by Penrose and Hameroff in the Orc-Or theory. Along the way, Nobel laureates and philosophers gathered at symposia, from the mystics and physicists' meetings of the 1970s to the science of consciousness conferences today, drawing dreamers and skeptics alike. For nearly 100 years then, the lines between the physics of the very small and the experience of the very conscious have remained hazy and contested. Some discoveries, such as the 1982 aspect experiment confirming quantum entanglement, or the growing evidence of quantum effects in biology, have only intensified interest. Yet, for every bold new theory, there remains a chorus of caution, reminding us that the science is far from settled. This blend of careful skepticism and visionary speculation has defined quantum consciousness theory since its earliest stirrings. The history tells us that, even as experimental tools and knowledge broaden, humanity's yearning to uncover the science behind our inner worlds continues, quiet as a sigh, insistent as a heartbeat, always drawing curious minds onward into the night. Gently now, let's explore what makes quantum physics so utterly special, those features that make it truly unique, and why they matter so much for the bold claims of quantum consciousness theorists. To many, quantum mechanics appears like a spellbook full of contradictions, yet its predictions have been tested to unprecedented precision. What, specifically, sets the quantum world apart from the classical realities that shape our daily lives and the way ordinary matter behaves, including your own brain cells? One of the most distinctive aspects is the principle of superposition. In the simplest terms, superposition means that a quantum object, say an electron or a photon, does not occupy a single state or position, but can instead exist in a blend of many possible states at once. A particle spinning both up and down, or occupying two paths simultaneously, challenges our everyday notions of things being in only one place or state at a time. This effect is more than just theoretical. It is directly observed in experiments like the famous double-slit experiment, where electrons fired at a screen create an interference pattern, evidence that each individual particle behaves, for a moment, as if it has passed through both slits simultaneously. Building upon this, quantum entanglement introduces a bond far deeper than what the classical world allows. When two quantum particles become entangled, their properties, spin, position, or polarization, are linked regardless of distance. If you measure one, the other's state is instantly determined, even if they are separated by the width of a laboratory or the expanse of Earth. In real experiments, physicists have entangled particles across hundreds and even thousands of kilometers, verifying that what happens to one immediately affects the other in ways that cannot be explained by signals traveling at the speed of light. This non-locality tears at the seams of classical physics, hinting at a universe where information, or at least the correlations between outcomes, can exist outside the boundaries of normal space and time. Another breathtaking property is quantum tunneling, where particles pass through barriers they should not, according to classical rules. In your body, quantum tunneling is essential for processes such as the fusion reactions within the sun, and for the chemical reactions that allow enzymes to catalyze life's essential functions. In technology, quantum tunneling enables devices like flash memory and explains why some electronic circuits have minimum feature sizes. Then there is the uncertainty principle. Articulated by Werner Heisenberg in 1927, this principle shows that some properties, such as a particle's location and momentum, cannot be known simultaneously to complete precision. The more closely you pin down one, the less clearly you can know the other. This is not merely a limitation of instruments, but a fundamental fuzziness built into reality itself. If you were to shrink inside your own brain to the level of its atoms, this uncertainty would mean that the positions of electrons and protons blur into clouds of probability. One more vital quality, quantum coherence. In a coherent state, quantum particles maintain their delicate superpositions, correlating their phases like synchronized swimmers executing a routine. Coherence is crucial for the operation of lasers, and in the future, for quantum computers. Yet coherence is easily lost by decoherence, the intrusion of the uncontrollable messiness of everyday reality, especially in warm, wet environments like the brain. Preserving quantum coherence is central to whether quantum effects could persist long enough within biology to matter for consciousness. What do these properties mean for the quantum consciousness hypothesis? Theorists wonder whether superposition could allow the brain to sample or entertain many possibilities at once before settling on a thought or decision. They imagine that entanglement could, in principle, provide the kind of holistic, integrated processing that consciousness seems to require, the binding of thoughts, sensations, and memories across distant brain areas into a unified experience. Quantum tunneling, meanwhile, might enable rapid, seemingly impossible exchanges within the brain's molecules. Critically, quantum features are not just mathematical curiosities. Some are harnessed in nature. For example, migratory birds navigate using entangled electron pairs in their retinas. Enzymes in biological cells exploit tunneling to speed up biochemical reactions far beyond what would be possible in a classical world. These real-world proofs embolden researchers to ask whether something equally extraordinary could be at work within the microarchitecture of your brain. Yet, these same quantum properties are also what make the quantum consciousness proposal so contentious. Can such fragile, fleeting effects endure amid the ceaseless electrical and chemical activity of living tissue? Most known quantum processes decohere in picoseconds, disrupted and lost to the background noise of temperature and molecular collisions. That is why the debate often turns to finding a plausible biological structure or process capable of protecting quantum states within the bustling wetland of the brain, a question we will soon approach. In essence, quantum physics represents a world in which certainty, locality, and singularity are abandoned in favor of probability, interconnectedness, and multiplicity. For consciousness researchers, the tantalizing hope is that these same qualities might just offer a path through the hard problem, explaining how your brain gives rise to the unique, integrated, and mysterious phenomenon of being you. As we drift onward, let us recall that these quantum features are not merely abstract. They underpin the operations of the universe and possibly, just possibly, the emergence of a mind capable of wondering at all. Among all the ideas proposed about how quantum physics might shape consciousness, one stands quietly at center stage: the Penrose-Hameroff orchestrated objective reduction theory, often written as ORC-OR. This theory is both pioneering and controversial, daring in its details while remaining deeply debated among neuroscientists and physicists alike. Let's settle in and unravel what Orch-OR really suggests, how it aims to connect quantum processes in the brain to the mystery of mind, and why its claims have attracted both admiration and skepticism in the scientific world. The story of Orch-OR begins in the 1990s, with the collaboration of two unusual partners. Roger Penrose, a brilliant British mathematician and physicist, renowned for his work on black holes and the nature of space-time, had long been fascinated by the hard problem of consciousness. Penrose doubted that the brain works purely as a classical computer, running predictable algorithms. He argued that conscious experience is not just information processing, but requires a special kind of physical event that is non-computable, meaning it could never be fully simulated or captured by a digital system. Penrose's intrigue with the quantum world came from the search for such true unpredictability, and with it, a foundation for conscious awareness. Enter Stuart Hameroff, an American anesthesiologist who had spent years studying the brain's cytoskeleton, the tiny structural framework inside neurons. Hameroff focused specifically on microtubules, tube-like protein structures within cells, far smaller than the cells themselves, whose functions seem to go beyond simple support. These microtubules are only about 25 nanometers wide, 1,000 times thinner than a human hair, yet they are essential for cell shape, division, and possibly information processing. Orchestrated objective reduction, as Penrose and Hameroff shaped it, is a two-part hypothesis. First, Penrose proposed that within certain biological structures, perhaps microtubules, quantum superpositions could occur and persist long enough to have effects at larger scales. That means a protein or a group of molecules in the brain could exist in multiple states at once, at least for brief periods. The objective reduction, or in the theory, is the process where this quantum superposition collapses, or becomes definite, not by external measurement or observation, but through the universe's own inner rules. Penrose suggested that when a quantum system reaches a certain threshold of complexity, gravity causes the wave function to collapse naturally, marking a fundamental moment of reality-shaping change. Hameroff joined this with the notion of orchestration. He hypothesized that the cellular environment, and perhaps the neuron itself, might guide and coordinate these quantum collapses, so they occur in synchrony, an orchestrated process, not just a cascade of random events. Together, these orchestrated collapses in the brain's microtubules would signal the birth of conscious events, your thoughts, sensations, and flashes of insight. The Orch-OR theory contends that consciousness does not emerge merely from neurons firing in patterns, as in the classical view, but from ultra-fast quantum computations happening inside the neuron's microtubules. These conscious moments arise when objective reduction occurs, potentially at scales of microseconds or faster, and the brain as a whole integrates these quantum events into subjective, unified experience. To make this a little more concrete, Penrose and Hameroff calculated the mass and arrangement required for such reductions to occur, suggesting vast numbers of microtubules across brain regions could participate, linking far-flung areas in quantum synchrony. They saw in this model a possible answer to the binding problem, how sights, sounds, thoughts, and feelings come together seamlessly, and perhaps even to the feeling of now, that ever-moving point where your conscious attention resides. Proponents of Orch-OR highlight fascinating observations. Microtubules are widespread, not only in neurons, but in most living cells. They are built from tubulin protein dimers, which can theoretically switch between different structural conformations, in a sense representing quantum bits, qubits, of information, though this remains speculative. The staggering complexity of the human brain, around 100 billion neurons, each with hundreds of millions of tubulin molecules, provides a vast stage for such computation, at least in theory. Orch-OR, if true, would mean that every conscious event is, at root, a quantum process, a self-collapse of space-time geometry occurring simultaneously in billions of microtubules, orchestrated by the unknown wisdom of the living brain. This would link the mind to the deepest architecture of the universe itself, through the quantum foundations of matter and gravity. Yet it is essential to gently note that the theory faces substantial skepticism. The brain is a warm, busy place. Quantum coherence and superposition are commonly destroyed in such environments, as we'll discuss soon. Most neuroscientists and quantum physicists argue that maintaining quantum states at biological temperature and complexity remains largely unsupported by current data. Still, experiments are ongoing, probing the behavior of microtubules, searching for quantum signatures within neurons, and testing whether biology has found a way to tame the quantum world. For now, the Orc-Or theory serves as a shining, if embattled, beacon for the possibility that consciousness may reach deeper than mere computation, right into the entangled, uncertain, and orchestrated heart of quantum reality itself. Whether or not it proves correct, it continues to evoke both scientific rigor and the timeless wonder of asking, could each moment in your mind be the echo of the universe's most fundamental quantum song? Let us now drift still deeper into the astonishing complexity within your own cells, focusing on the star structure of quantum consciousness theory. Microtubules. Understanding these remarkable molecules and their real biological roles helps clarify both the imaginative reach and the practical challenges of proposals like Orch-Or. Settle in and let's explore what microtubules truly are, how they function in your brain, and why theorists believe they could be a secret gateway to quantum mind. A microtubule is a hollow, cylindrical filament made from repeating units of a protein called tubulin. Each microtubule measures about 25 nanometers across, so small that 1,000 would fit within the width of a human hair. In the brain's vast landscape, microtubules are everywhere, inside every neuron, branching outward like scaffolding from cell body to the tips of far-reaching axons and dendrites. They belong to the cell's cytoskeleton, the internal support structure that gives a cell its shape and helps it resist life's constant mechanical stresses. Beyond simple support, microtubules are crucial for the neuron's internal logistics. They act as express highways, along which engine-like proteins, such as kinesin and dynein, haul precious cargo, nutrients, neurotransmitters, and sometimes entire organelles, between the cell's nucleus and its remote outposts. At the tips of axons, where nerve cells communicate, microtubules help maintain structure and enable rapid signal changes. In the developing brain, microtubules play an even more astonishing role. They guide the migration of neurons, shape the complex folding of the cortex, and choreograph the intricate wiring that will allow you to see, move, think, and dream. Microtubule dysfunction has been linked to some devastating diseases. For example, in Alzheimer's, a protein called tau becomes disordered, causing microtubules to collapse and neurons to die. But what does this have to do with quantum consciousness? Enter the hypothesis of Penrose and Hameroff. They pointed out that microtubules are not simply static structures, but are built from tubulin dimers, pairs of tubulin molecules, each of which can, in theory, switch between two or more conformational states. This switching, occurring on nanosecond timescales, might serve as a kind of binary or qubit element with the potential to support quantum superposition. In this view, the interior of a microtubule becomes a candidate environment for quantum effects. The geometry is highly ordered, the local electrochemical fields are intense, and the repeating protein units might shield quantum states, at least temporarily, from environmental disturbance. According to Orch-Or, orchestrated quantum changes in the tubulin structure across many microtubules could not only store information, but integrate it at quantum speed and scale. In theory, billions of tubulin qubits could interact across the vast landscape of the brain, encoding and binding the contents of experience far more efficiently than any classical network could explain. Scientists have observed that microtubules exhibit fascinating collective behaviors. In test tubes, they oscillate in electrical patterns when stimulated, for reasons not fully understood. Spectral properties of tubulin imply they may interact with photons, tiny packets of light, suggesting a potential for rapid light-based signaling. Optical studies hint at the possibility of biophotons, communicating within and between cells. However, whether these are truly quantum processes remains uncertain. A compelling aspect of microtubules is their central role in anesthesia. Drugs that cause loss of consciousness, like some general anesthetics, are known to bind to tubulin and disrupt microtubule function. Hameroff and others have argued that this link places microtubules at the very heart of conscious experience, as disturbances in their activity lead directly to the unconscious state. Despite these tantalizing possibilities, most molecular biologists see microtubules as vital but classical structures, marvels of construction and engineering rather than computation or quantum information. They emphasize the relentless motion, high temperature, and molecular chaos present in living brains would likely destroy delicate quantum effects before they could influence brain-wide activity. As of today, quantum coherence in microtubules at timescales relevant for neurophysiology has yet to be observed experimentally. Nonetheless, ongoing research continues. Recent studies probe the vibrational and optical properties of tubulin, hoping to catch hints of quantum coherence. Experimental designs now measure picosecond and even femtosecond timescale changes in living cells, aiming to uncover whether microtubules are quietly computing in the quantum realm, or if they serve instead as nature's ultra-reliable construction beams and logistics lines. Some labs are even examining quantum tunneling in biological proteins, inspired by microtubule research. Bringing it back to you, the listener, your own consciousness depends every second on the seamless functioning of microtubules, guiding the shape of neurons, the speed of thought, and the maintenance of memory. Whether or not they harbor quantum effects that explain awareness, they remain a marvel of molecular engineering, proof that the building blocks of your mind are endlessly fascinating, carrying out millions of complex dances each second within the glowing world of your brain. As we move forward, remember, arguing for quantum mind requires not just elegant theory, but also a way for quantum processes to endure and matter inside biology. That, as we will soon discover, brings us to the profound challenge of decoherence, a major scientific hurdle for quantum consciousness ideas. Now let us softly approach the scientific crossroads where quantum consciousness theories meet perhaps their greatest challenge, a barrier known as decoherence. In the hopeful visions of quantum consciousness, effects like superposition and entanglement are imagined to flicker within the brain, holding information and binding the contents of awareness. But to truly understand whether this is possible, we need to consider what happens to quantum states in the untidy, high-energy environment of living tissue. Decoherence is the process by which quantum systems lose their uniquely quantum properties, like existing in multiple states at once or being entangled with distant partners as they interact with their environment. In essence, decoherence marks the transition from the bizarre wonderland of quantum physics to the familiar predictability of classical physics. It is not an explosion or a sudden snap, but a rapid, relentless fraying of coherence, a scattering of delicate quantum information into the noisy background of the world. Why does decoherence matter so much for the quantum mind? The answer lies in the extraordinary sensitivity of quantum states. For particles in a laboratory, quantum behaviors such as superposition can only be preserved when the system is exquisitely isolated from the outside world, chilled near absolute zero, shielded from disruptive photons and vibrations, and protected from stray atoms, heat, and motion. Even a single interaction with the environment, a random jostle, a photon absorbed or emitted, a collision with a water molecule, is usually enough to destroy a quantum state, forcing it to collapse into a definite classical outcome. Consider the timescale. In typical biological environments, decoherence occurs astonishingly fast, often in less than a trillionth of a second, a picosecond, or even a femtosecond. In contrast, the functions of neurons, like firing signals, integrating information, or changing state, operate over milliseconds, thousands or millions of times longer. This yawning gap in timescale presents a formidable problem. If a quantum state survives only for a picosecond before collapsing, how could it influence the action of cellular machinery, let alone merge into a flowing conscious experience that persists for seconds, minutes, or an entire waking lifetime? In the case of the Penrose Hameroff or theory, advocates point to microtubules as potential sanctuaries for quantum superposition. Careful calculations, however, suggest that even the ordered interiors of microtubules, surrounded by the watery, electrically noisy cytoplasm, are subject to relentless decoherence. The combined effects of thermal vibrations, electromagnetic noise, and the busy chemical traffic inside every cell are likely to collapse quantum states in picoseconds or less, far too fast for coordinated events to influence the brain as a whole. Scientists have probed these issues with sophisticated models. In 2000, physicists Max Tegmark and John Joe McFadden independently analyzed whether quantum states could persist in microtubules under physiological conditions. Their results were sobering. Even under optimal circumstances, decoherence would destroy fragile quantum effects far faster than needed for neural computation. Critics also point out that known quantum computers, machines built in controlled sub-zero environments, struggle to maintain coherence even with enormous effort and technology. The comparative chaos of biology seems, for now, even less forgiving. Proponents of quantum consciousness are not discouraged, and the story is far from finished. Some have proposed that biology may have evolved unknown mechanisms to minimize decoherence, perhaps through clever structural arrangements, shielding, or ultra-fast cycles that refresh quantum states before they fade. Others argue that environmental noise itself can sometimes stabilize certain quantum systems, a process called decoherence avoiding subspaces, which, if true, might suggest biology has discovered quantum tricks yet to be fully understood. Recent work in fields like quantum biology has revealed, for example, that some photosynthetic systems can preserve quantum coherence at room temperature, though for much shorter durations and typically in simpler, smaller systems than a neuron. The question of decoherence, then, sits quietly at the heart of the debate. It invites a careful balance of imagination and skepticism. Yes, quantum effects underpin the universe, and yes, biology uses quantum mechanics in certain remarkable ways. But for quantum consciousness theories to hold, researchers must demonstrate not only that quantum events can occur in living tissue, but that they can persist, coordinate, and influence neural activity in ways that classical models cannot match. As a gentle metaphor, decoherence is like trying to keep a soap bubble intact in a hurricane. The bubble's fragile beauty is real, but the surrounding forces tear it apart almost instantly. For the quantum mind to become more than theory, scientists must show how nature might shelter such fragile effects, letting them grow large enough to shape experience. Yet the investigation continues with cautious optimism. Advanced measurements probe ultra-fast vibrations and energetic states inside living cells. The search for quantum coherence in biology is ongoing, and each new discovery pushes the question a bit farther. Is the mind a quantum symphony, or is it the result of astonishingly complex but ultimately classical neural harmonies? For now, the problem of decoherence stands as both guard and gateway in our search for the quantum brain, a challenge at the frontier of what science dares to imagine, awaiting resolution as quietly as a scientific whisper in the dark. Let us now ease into one of the most enchanting and perplexing features in all of quantum physics, a phenomenon whose reputation for mystery has spread far beyond laboratory walls: quantum entanglement. Grasping the essence of entanglement helps us understand why some believe it might point the way toward a radically new vision of the mind, in which your consciousness could, at least in principle, be correlated with distant regions of the universe. In the simplest terms, quantum entanglement is a special connection between two or more particles, such that their properties become tightly linked regardless of the distance separating them. Imagine two electrons, for instance, born from the same interaction. According to quantum theory, their states, like their angular momentum or spin, are described by a single shared wave function. If you measure one electron and find it spinning up, you immediately know, no matter how far away, the other is spinning down. What makes this genuinely astonishing is that, until measurement, neither particle has a fixed spin. It is only their mutual relationship, enshrined in the mathematics, that is definite. This might sound like an odd curiosity, but the implications are profound. Albert Einstein, who famously doubted the weirdness of quantum mechanics, derided entanglement as spooky action at a distance. Yet decades of precise experiments, beginning with Alain Aspect's tests in the 1980s, have confirmed that these correlations are real. Quantum entanglement works, and its predictions have been validated to a degree that leaves little room for skepticism in physics. But why does this matter for the theory of quantum consciousness? Advocates like Penrose, Hameroff, and others have speculated that, if entanglement can link quantum bits of information across vast distances, perhaps it might also operate between quantum states within the brain. In other words, entanglement could serve as a bridge between groups of molecules, or even between different regions of the brain, tying together information streams in a way classical connections never could. This, they propose, might explain the peculiar wholeness or unity of conscious experience, why our senses and memories appear bound so seamlessly, even as their neural origins are widely distributed. Some theorists even go as far as to wonder if entanglement, should it exist on a significant scale in the brain, could provide channels for non-local communication or synchrony, not only within a single person's skull, but, at the very edge of speculation, between different conscious beings, or even between mind and universe. While such ideas are breathtakingly bold, it is crucial to emphasize that no scientific evidence currently supports entanglement on this macro scale among human brains or between people across space. For now, this remains imaginative territory, not established fact. Within the realm of biology, however, there are authentic and exciting examples where entanglement may play a functional role, though not, as yet, in the brain. Researchers studying avian migration have found that the eyes of some birds may use entangled electron pairs to sense magnetic fields, a quantum trick that helps them navigate across continents. In plants, quantum effects, conceivably including fleeting entanglement, enhance the transfer of energy during photosynthesis, increasing efficiency well beyond what classical chemistry alone could manage. But the brain situation is far more challenging. Entanglement, like all quantum effects, is fragile. It is easily disrupted by the warmth and chaos of living cells, a process, as we have learned, called decoherence. Even in the microtubules cited by Penrose and Hameroff, maintaining entanglement over biologically meaningful timescales is hotly debated. Current experimental evidence provides no robust proof that organized, enduring entanglement exists within the human nervous system. Most physicists believe that any entangled states in the brain would dissipate in picoseconds, billions of times faster than a neuron can fire. Nevertheless, this conversation remains open for two reasons. First, quantum research has repeatedly overturned what was once thought to be impossible, from entangling particles across laboratory benches to doing so across satellites orbiting Earth. Second, novel discoveries in quantum biology have shown that nature sometimes finds unexpected ways to preserve quantum phenomena, leading some to believe that unexplored mechanisms could exist in more complex organisms, including perhaps in you. Entanglement remains an evocative metaphor for connection, a hopeful hint that, on the deepest level of physical reality, separateness may be an illusion. For quantum consciousness theorists, the dream is that one day we may discover processes linking regions of the brain, or even the brain and cosmos, in far more mysterious ways than we can currently observe. For now, as science gently but firmly pursues its questions, entanglement stands as a real quantum phenomenon with breathtaking implications, just not yet a proven bridge between your mind and the remote corners of the universe. As you rest in this quiet assurance, it is calming to know that at the core of matter, particles remember their partnerships, no matter the distance, a testament to the universe's capacity for connectedness, and a soft nudge to wonder what mysteries may still be waiting quietly within your own inner world. Let's gently turn our attention to the realm of scientific experiments and evidence, the careful, methodical testing that moves ideas from speculation to established or refuted fact. The question of whether quantum effects operate within the brain and whether they truly influence consciousness is one of science's boldest frontiers. In this hush of night, we can trace what research has been done, what has been claimed, and what still eludes our patient gaze. First, It is important to recognize the types of evidence quantum consciousness would require. Discovering quantum behavior in the brain means, at minimum, observing clear, persistent phenomena such as superposition, coherence, or entanglement among molecules, proteins, or larger structures like microtubules, over timescales long enough and distances broad enough to affect neural computation and, by extension, conscious thought. This is a tremendous experimental challenge, as the signals scientists seek are subtle, fleeting, and easily swamped by the background noise of biological activity. Over the last 20 years, several lines of investigation have sought to close this evidence gap. Early on, interest focused on detecting quantum coherence or quantum signatures in brain tissue. Researchers have used ultra-fast spectroscopy, attempting to spot minute changes in how microtubules or tubulin proteins vibrate and interact with light. In some test tube experiments, certain quantum-like oscillations were observed in isolated proteins at very low temperatures, conditions largely unlike the bustling warmth of the living brain. More recently, a handful of studies have tried to spot quantum effects in living neurons or brain slices. For example, some researchers have reported faint photon-like signals, biophotons, being emitted and transmitted between cells, raising intriguing questions about whether light-based signaling might support fast information transfer. There are experiments showing that microtubules can affect the speed and propagation of electromagnetic waves in controlled settings. But whether these are quantum effects, classical phenomena, or something else entirely remains under debate. Some of the most exciting discoveries in quantum biology come from outside neuroscience. In photosynthesis, plant proteins conduct energy with a speed and efficiency only explicable by quantum coherence, energy moving as a wave through the light harvesting complex, not hopping unevenly as classical chemistry would dictate. The European Robbins compass sense is now thought to depend on entangled electron pairs reacting to Earth's magnetic field. These findings, real concrete quantum phenomena in biological systems, demonstrate that tiny pockets of life can indeed access quantum effects, suggesting that nature can sometimes solve the problem of decoherence. And what about the Orc-OR theory's specific predictions? Penrose and Hameroff's model has inspired new types of experiments, searching for rapid oscillations in microtubule arrays, or for anesthetic effects resulting directly from disruptions to microtubule function. Some studies have linked changes in microtubule behavior to shifts in brain state under anesthesia, but critics caution, causality and quantum involvement remain unproven. What remains conspicuously absent from the scientific record is direct, repeatable evidence of large-scale, enduring quantum coherence or entanglement in any living brain. Attempts to measure superposition in microtubules or neurons, especially at body temperature and in the presence of metabolic activity, have thus far turned up empty. The best current understanding is that quantum effects, if they exist in the brain, would be brief, local, and most likely filtered out before influencing awareness. It is essential, in this gentle inquiry, to remember that the lack of evidence does not necessarily mean quantum consciousness is impossible, only that, with current tools and techniques, its core claims remain unproven. Scientists have become skilled at detecting quantum behavior in ultra-pure crystals, in superconducting circuits cooled to near absolute zero, and in isolated protein complexes. But the living brain presents a vastly more dynamic and chaotic cauldron, complicating each attempt at quantum measurement. Nevertheless, the field is by no means stagnant. New tools, from femtosecond lasers to advanced quantum sensors, become available each year, gradually allowing more refined exploration at the intersection of biology and quantum physics. Animal models, brain organoids, and even engineered molecular systems are being assembled to probe for elusive quantum whispers. Much like listening for faint echoes in a bustling orchestra, one of science's strengths is its patience. It is possible that one day, experiments may reveal unknown mechanisms that harness quantum features in the brain, transforming speculation into fact. Or it may be that consciousness is the outcome of an intricate but classical dance, wondrous without needing quantum choreography. For now, the search for direct evidence of quantum mind remains one of the most fascinating and difficult quests in all of science. like searching for a faint pulse in a sea of living, dreaming, and deeply mysterious noise. As you drift a little further into relaxation, rest in the quiet honesty of where the evidence stands. Tantalizing glimpses, robust discoveries in other living systems, enduring challenges for brain research, and above all, a spirit of humble inquiry, a willingness to follow the evidence wherever it leads, even if the answers require us to wait, to listen longer, and to continually refine our questions about the deepest workings of mind and reality. As we let our minds wander through the landscape of quantum consciousness, it's time to quietly consider the voices of skepticism and scientific critique. In science, every bold hypothesis is tested and retested, not only by fresh experiments, but by rigorous questioning from peers, experts who seek logical consistency, plausible mechanisms, and clear evidence. For quantum consciousness theories, the scrutiny has been especially intense, revealing both conceptual challenges and practical obstacles that remain unresolved. Many neuroscientists and physicists begin their criticism at the level of biological feasibility. They point out, with cautious clarity, that the conditions required for stable quantum effects, like superposition, entanglement, or coherence, are extremely fragile. In the warm, wet, and electrically noisy environment of the brain, molecules are constantly colliding, temperature fluctuates, and energy pulses back and forth on every scale. Extensive theoretical modeling, notably the work of Max Tegmark in the early 2000s, calculated that in brain-like settings, quantum superpositions would decohere in less than a trillionth of a second, far shorter than neurons or microtubules could possibly maintain meaningful, coordinated events. Critics argue this decoherence would erase quantum information long before it could integrate into conscious thought or shape perception. Next, skeptics examine the specific biological claims made by advocates of quantum mind, especially in the Orc-OR theory. While microtubules are indeed vital for cell structure, transport, and developmental signaling, no robust experimental evidence demonstrates they serve as conduits for quantum computation in living brains. Tests with anesthetics, while showing these drugs can disrupt microtubule function and consciousness, have yet to establish that the effects are genuinely quantum rather than the result of broader biochemical disturbances. Additionally, the idea that tubulin molecules act as quantum bits or qubits is questioned by structural biologists who note that most protein motions are best described by classical physics, with quantum effects operating briefly at the chemical bond level, but not persisting long enough for information processing. Conceptual critiques also abound. Leading philosophers of mind argue that invoking quantum processes does not automatically bridge the notorious hard problem of consciousness: why and how physical processes are accompanied by subjective experience. Questioning whether quantum phenomena could be necessary or sufficient for conscious awareness, they remind us that quantum physics, while fascinating, addresses the behavior of particles, not the qualitative qualities of experience, the sense of sight, pain, or memory. Such properties still appear to skeptics as brute facts, not illuminated by physics alone. Further, many experts see a kind of gap in the logic of quantum mind proposals. Describing complex biological structure and suggesting that quantum information could exist is not, they argue, the same as demonstrating it plays a critical role in higher cognitive functions or awareness. In other words, quantum phenomena may be present at the level of atoms and fundamental bonds, as in all matter, but that does not automatically mean they are orchestrated, integrated, or sustained within the macroscopic networks of the brain. There are also practical critiques rooted in the philosophy of science. A theory should not only be internally consistent and compatible with known data, but it should generate clear, testable predictions. Critics point out that many quantum consciousness hypotheses have struggled to do this with sufficient specificity. If a claim cannot be falsified, if every outcome is somehow explainable by hidden quantum effects regardless of observation, it risks sliding from science into speculation. Skeptics hence call for proposals that can be probed, measured, and potentially disproved in the lab or clinic. Adding to these scientific checks are concerns about misunderstanding or misusing quantum ideas. The terms quantum, entanglement, and collapse have for decades drifted into popular culture and alternative health claims, sometimes stripped of their actual scientific meaning. True skepticism in science, therefore, urges a cautious separation of beautiful metaphors from verified, mechanistic models. Yet, it's important to recognize that most critics do not dismiss the possibility of quantum effects in biology altogether. The robust fields of quantum biology, quantum chemistry, and molecular physics continue to reveal quantum phenomena in many living systems, from photosynthesis to olfaction to enzyme reactions. Rather, their skepticism targets the leap from quantum interactions at microscopic scales to the origin of consciousness itself, a leap for which the current chain of experimental and theoretical evidence remains incomplete. In the quiet atmosphere of scientific progress, this skepticism is necessary, even comforting. It keeps the discipline honest. It ensures that hope and curiosity are always tempered by careful reasoning and respect for what has and has not been shown. Many pioneers, after all, find their boldest ideas challenged, reshaped, or even replaced as evidence accumulates. A process that brings science closer, not just to wonder, but to the truth that underlies it. So as we lie back and listen to the litany of critique, it is not with discouragement, but with the gentle patience of those who know that every grand idea must first survive the most careful and caring scrutiny. The dream of quantum consciousness may yet reveal new insights, or it may give way to alternate explanations that illuminate the age-old mystery of the mind. In either case, science continues to seek, to question, and to awaken us with every new challenge to the marvel of the search itself. Let's take a peaceful breath and look now at where quantum effects have been undeniably found in living things, outside the brain, a field now called quantum biology. The existence of real, functional quantum phenomena in nature powerfully shapes the debate. It shows that life, in certain cases, has learned to harness the weirdness of quantum physics, not just in controlled laboratory experiments, but in evolution's workshop, scattered across the tree of life. Perhaps the most celebrated example is the process of photosynthesis, the ancient energy harvesting mechanism that powers nearly all life on Earth. In the light harvesting complexes of green plants, scientists have found evidence of quantum coherence. When sunlight strikes a leaf, energy is transferred through chains of pigment molecules towards chemical reaction centers. Ultra-fast laser experiments reveal that this energy transfer does not always occur in a straight classical path, jumping from one molecule to the next like a baton passed in a relay race. Instead, the energy seems to travel as a wave, simultaneously exploring multiple possible routes through superposition, searching out the most efficient path. This quantum efficiency allows plants to harvest light with a remarkable success rate, significantly higher than would be possible by classical means alone. Animals too exploit quantum physics. Migratory birds like the European robin navigate across continents using Earth's magnetic field, a task that for many years baffled researchers. Recent evidence points to a quantum compass in the bird's eye. Entangled electron pairs, formed in special proteins called cryptochromes, respond to subtle changes in magnetic orientation, giving the bird an inner sense of direction. Quantum entanglement here persists for microseconds, a surprisingly long time compared to the tallies seen in other warm, disordered biological settings. Another fascinating frontier is olfaction, or the sense of smell. The traditional account holds that odor molecules bind to receptors by shape alone, like keys fitting into locks. However, some researchers have proposed that receptors may also be sensitive to the quantum vibrations of molecules, explaining why certain similarly shaped chemicals smell very different, and why isotopically labeled molecules, nearly identical save for a few neutrons, sometimes emit surprisingly unique scents. Experimental support is still debated, but quantum tunneling, where electrons jump across energy barriers within the receptor, is a candidate mechanism. Even inside your own body, quantum tunneling facilitates essential chemical reactions. Enzymes, those catalytic powerhouses of the cell, often rely on electrons tunneling through energy walls to trigger changes in target molecules, dramatically speeding up metabolic processes. Without quantum tunneling, many life-giving reactions would happen millions of times more slowly, making life as we know it impossible. What do these discoveries mean for the debate about quantum mind? They show indisputably that quantum mechanics is not confined to laboratories or to the far reaches of the cosmos. In nature, there exist specific settings, typically involving ordered molecular structures, ultra-fast timeframes, and importantly, biological utility, where quantum effects are not just present, but essential to the organism's function. And yet, these effects are all local, rapid, and focused. A photosynthetic protein may sustain coherence for nanoseconds. A bird's cryptochrome may foster entanglement for microseconds. What unites these examples is that the quantum states they depend on are shielded from environmental noise by exquisitely tailored microenvironments. Even here, life's quantum exploits are fleeting compared to the timescales and global integration required for brain processes like consciousness. Quantum biology suggests a kind of cautious optimism. It powerfully disproves the old assumption that quantum effects are always destroyed by the messiness of life. It also supports the idea that evolution may find, in very precise circumstances, ways to nurture quantum states for as long as needed and no longer. But so far, no study has offered robust, repeatable evidence for quantum coherence, superposition, or entanglement operating at the scale or duration required for human consciousness. Still, the lessons are invaluable. The search for quantum mind has borrowed ideas and techniques from quantum biology, methods for measuring ultrafast energy transfer, modeling protein structure, and observing faint photonic or electronic interactions. Each advance in quantum biology hints that tomorrow's discoveries may uncover, in places not yet imagined, new ways that life spins the quantum coin and wins. As the evidence stands tonight, nature's embrace of quantum weirdness is proven and profound, but carefully circumscribed. You, as a living being, are already the beneficiary of quantum phenomena. Your breath fueled by photosynthetic plants, your energy cycles quickened by tunneling enzymes, your nights perhaps illuminated by the magnetic whispers heard by birds overhead on their journeys. Whether your own brain has found yet another layer of the quantum toolkit, and whether this could be the missing piece in the puzzle of consciousness, remains among the questions that gentle science still pursues. As our exploration continues, let's gently turn our minds to the landscape of alternative theories, other scientific ideas that seek to explain consciousness without invoking quantum physics. Revisiting these perspectives is a reminder that, while quantum consciousness theories are bold and imaginative, the scientific search for the origins of awareness is broad, methodical, and deeply creative. One of the most influential frameworks today is the Integrated Information Theory, or IIT, proposed by neuroscientist Giulio Tononi in the early 2000s. IIT posits that consciousness is a property of systems that achieve a very particular kind of information integration. Imagine many individual components, neurons, or even circuits, combining and linking their information in ways that form a single, unified whole. The measure of phi, central to IIT, quantifies how much a system's information is integrated and irreducible to its parts. If a network possesses a high phi, IIT proposes, it possesses a high degree of intrinsic consciousness, regardless of whether quantum effects are involved. This theory has inspired new approaches in brain imaging and even speculation about artificial consciousness. Another perspective, known as the Global Workspace Theory, GWT, was originally conceived by cognitive scientist Bernard Baars and further developed by neuroscientists such as Stanislas Dehaene. GWT envisions the brain as a kind of theatre, where many unconscious processes occur behind the scenes, but only certain information is broadcast across a global workspace to become accessible to our subjective awareness. In this view, consciousness arises not from the fine details of microphysics, but from large-scale synchronization and integration among brain regions, especially involving the prefrontal cortex and its ties to perception, memory, and decision-making. A third cluster of ideas comprises higher-order theories of consciousness, which suggest that awareness requires not only sensory or emotional input, but also the brain's ability to create representations of its own states, to think about thinking. These theories, developed by philosophers like David Rosenthal and neuroscientists, such as Joseph Ledoux, propose that your consciousness emerges when the brain steps back, in a sense, and surveys its own activity. Predictive processing and free energy principle models, articulated by theorists like Carl Friston, further add to the rich tapestry of explanations. In these views, the brain is an active prediction engine, using top-down models to constantly anticipate, compare, and minimize the difference between expected and actual sensory input. Conscious perception is then the outcome of this dynamic, self-updating model, again, a result of complex computation rather than fundamental physics. It's worth noting that many of these alternative theories are being tested with cutting-edge neuroimaging and computational modeling techniques, offering increasingly fine-grained accounts of which patterns of neural activity correlate with conscious and unconscious states. For example, brain scans of people under general anesthesia, patients in coma, or those in non-REM sleep reveal measurable changes in connectivity and synchronization, supporting the link between consciousness and network-level brain activity. Some philosophical theories, meanwhile, sidestep questions of mechanism altogether. Panpsychism, revived in recent years by figures like philosopher Philip Goff, suggests that consciousness may be a fundamental property of all matter, present even in the simplest particles, though in forms unimaginably different from human awareness. Others, such as Daniel Dennett, argue that consciousness is a kind of illusion, a narrative spun by competing processes in the brain, only seeming unified because our minds evolved to stitch fragments together into a continuous sense of self. Importantly, none of these alternative theories deny the wonders of quantum mechanics or its necessity for the existence of the universe's building blocks. They simply argue that the intricate binding that underpins conscious experience is likely a result of scalable interactions among classical systems, the coordinated lacing of neurons, synapses, and circuits, rather than quantum dances at the molecular level. These frameworks offer a gentle counterpoint to quantum mind theories, providing roadmaps for research that emphasize emergence, computation, network complexity, and even self-referential processing. They each offer strengths and face their own conceptual and experimental hurdles. Some explain aspects of consciousness, such as global accessibility, integration, or the unity of experience, with remarkable precision, but still leave the hard problem unanswered. Others inspire new lines of experimentation in artificial intelligence, brain-machine interfaces, and neuropsychiatric medicine, revealing the practical power of classical approaches. So, as you settle into this night's reflection, you can rest in the awareness that the scientific study of consciousness is rich, multidisciplinary, and vibrantly contested. Whether ultimate answers will come from quantum mechanics, advanced computation, emergent network dynamics, or something yet unseen, what is certain is that searching for the source of mind has kindled some of the greatest creativity and collaboration in all of science. These many perspectives, woven with care and humility, continue to shine gentle light on the mystery we all share, the experience of being, and the quiet question of what it means to be conscious at all. As we ease deeper into the question of your brain's relationship to the universe, let's quietly consider the bold speculation that the brain might work, in at least some ways, like a quantum computer. Quantum computing is a field that fuses information science with quantum physics, creating machines that do not merely process binary ones and zeros as classical computers do, but use the features of superposition and entanglement to operate with quantum bits, qubits, that can represent multiple states simultaneously. This, at least in theory, allows quantum computers to solve particular classes of problems exponentially faster than any conceivable classical device. Within the quantum consciousness community, the idea surfaces that the brain, with its fantastically complex and densely connected architecture, could exploit similar principles. Might your mind operate as a quantum computer, leveraging the fluid logic of the quantum realm to achieve feats of creativity, intuition, or the unity of experience that classical models find hard to explain? To probe this possibility, let's gently lay out what makes quantum computing unique, see how this compares to neural information processing, and examine what science has discovered so far. Quantum computers use qubits which, because of superposition, can be both on and off at the same time. With entanglement, they link information non-locally, correlating outcomes in ways that defy classical explanation. Algorithms like Shor's, for factoring huge numbers, and Grover's, for searching data, reveal mind-boggling speed-ups for certain tasks. Crucially, however, today's quantum computers require extreme conditions: vacuum chambers, temperatures close to absolute zero, and elaborate shielding to stave off decoherence. Even then, the largest working devices can only manage a few dozen to a few hundred qubits for extremely short timescales. By contrast, your brain is a warm, self-organizing network made up of about 86 billion neurons, each connecting on average with thousands of others. The computing nature of the brain comes from the interaction of biochemical signals, the flow of ions across membranes, and the remarkable modulation of network-level patterns. The brain is massively parallel, able to process vast swathes of information at once. It possesses extraordinary fault tolerance, and it exhibits flexible, emergent behavior, qualities quantum computers aspire to, but achieve via different physical principles. Could the brain's microtubules, as suggested by Penrose and Hameroff, act as biological qubits, resisting decoherence long enough to perform quantum computation? Theorists have estimated, using optimistic calculations, that the combinatorial power of billions of microtubules and trillions of tubulin molecules could, in principle, allow quantum computations beyond the reach of current artificial devices. The appeal is obvious. Consciousness could be the readout of a grand biological quantum computer, binding information holistically and even accessing non-local correlations, explaining the sense of unity, spontaneity, and boundless creative intuition that mark human awareness. However, evidence for real quantum computation in the brain is, at this point, indirect and highly contentious. Most neuroscientists argue that what the brain does so elegantly, pattern recognition, associative memory, rapid decision-making, emotional nuance, can and is explained by classical mechanisms. Neural networks, even running on digital computers, achieve impressive feats in perception and learning, hinting at the sufficiency of well-tuned, large-scale classical processing. The speed of consciousness, for example, your ability to recognize a face, generate a creative idea, or shift attention, correlates more tightly with traditional brain rhythms and electrical activity than with any known quantum process. Moreover, as we've seen, maintaining the delicate quantum states needed for computation is tremendously difficult in artificial systems, and seems even less likely in biological tissue, where collisions, heat, and noise are rampant. Experiments looking for explicit markers of quantum computing, like long-range entanglement, widespread coherent oscillations, or quantum error correction, have not found clear signatures in the brain. Critics thus view quantum computer models of mind as beautiful hypotheses lacking robust empirical grounding. Still, the analogy remains compelling for many. It invites us to imagine that consciousness is not a hardwired program, but a kind of living algorithm, a web of ongoing, self-tuning computation that occasionally gestures toward quantum possibilities. Even without confirmed quantum computation, aspects of quantum-like logic may inspire new theories of mind, artificial intelligence architectures, and models of perception and memory. In parallel, research on actual quantum computers continues, driven both by their practical promise and by curiosity about what they teach us about information and reality. Should future experiments unveil unexpected coherence or computational tricks in biological networks, the door would open wider to real, testable quantum models of the brain. For now, though, the quantum computer hypothesis for mind remains a fascinating idea, a gentle incitement to keep asking how your experience emerges from matter, and whether the deepest registers of your awareness might, after all, resonate to the same quantum harmonies as the universe itself. In the long, quiet night, these questions remain among the most beautiful and most elusive that science has ever asked. Now let's gently draw our thread back out, widening our lens from the intricate micro-worlds within your brain to the sweeping canvas of the universe itself. If quantum consciousness theories hold any truth, if the workings of your mind indeed rely on quantum phenomena, what does this suggest about your potential connection to the cosmos? Could it be that your awareness is, in some deep sense, entangled with the fabric of reality on the largest possible scale? Quantum physics teaches us that at the most fundamental level, everything in the universe is woven from the same quantum rules. Atoms in your brain and atoms in distant galaxies abide by the same strange laws: superposition, entanglement, and waves of probability linking near and far. The non-local nature of entanglement, where pieces of information can be instantly correlated across vast distances, has prompted some researchers to muse on the possible oneness of reality. In this vision, if quantum effects inside your brain play an active role in consciousness, your mind is not cut off in isolation, but is itself a ripple or process within a much broader quantum tapestry. Consider, for a moment, the implications of this for consciousness. If Orch-or or similar theories are correct, then conscious moments might not be simply contained within your skull. They could be objective reductions of quantum states across microtubules, collapses that, according to Penrose, are anchored to the fundamental structure of space-time itself. Every flicker of conscious awareness would be not only a private event, but an action upon the very geometry of reality. In this way, each act of perception or thought becomes a tiny imprint on the universe, a suggestion that at the smallest scales, your experience participates in cosmic unfolding. Some theorists have gone further, speculating that consciousness could be a universal feature, what philosopher David Chalmers and others call panpsychism. In this perspective, the property of experience may be built into the universe at the quantum level, present, though in primitive forms, wherever quantum systems exist. Your brain, then, does not generate consciousness from nothing, but localizes and intensifies an awareness scattered throughout the cosmos, gathering the raw potential into the vivid self-aware experience you know as your own mind. It's a vision as ancient as it is modern. Throughout history, philosophies from Vedanta to Stoicism have hinted at some deep unity between the mind and the order of nature. Quantum consciousness theory gives this an empirical twist, presenting the possibility that brains, as highly organized quantum systems, reach into the depths of cosmic law, reading out the fabric of reality in conscious moments. Still, as tempting as these images may be, it is essential to distinguish what is known from what is speculation. There is as yet no experimental evidence that your brain's quantum states interact directly with distant parts of the universe, or that human minds are entangled in a literal quantum sense with the cosmos. The scaling challenge remains immense. Quantum effects, as observed, are exquisitely delicate and typically lost in the noisy heat of biological life. Most contemporary physicists see quantum non-locality as a feature for particles and simple systems, not a mechanism that links minds across space and time. Nevertheless, the possible implications are profound, even if the details remain uncertain. If even a trace of quantum coherence or entanglement operates in the brain, then consciousness might be understood not merely as a private, isolated process, but as linked in some deep way to the ongoing process of the universe. Thoughts, sensations, and awareness would not simply occur in a vacuum, but would reflect the play of quantum fields that pervade matter, energy, and space itself. For now, as you settle deeper into this night's journey, you can reflect on the beautiful mystery that every atom in your body once belonged to the heart of a star. Every breath is linked by biology and chemistry to all of life, and perhaps every moment of mind is nestled within the subtle webwork of the universe. The question, is your brain connected to the universe, is, at its most profound, a humble invitation to see your existence not as a solitary spark, but as a pattern in a cosmos that is everywhere, alive with possibility, with mystery, and possibly with consciousness in its most fundamental forms. Let us quietly ponder what all of this might mean for you, not in distant, abstract terms, but in the gentle immediacy of your own lived experience. The question of whether your brain could be quantum connected to the universe isn't just a scientific curiosity. It ripples into the heart of how you understand yourself, your sense of free will, and even your view of reality itself. For many, the classical picture of the brain offers comfort. The mind as a sophisticated machine, its patterns dictated by neural networks and electrochemical signals, its outcomes explainable by cause and effect. This vision brings with it the promise of clarity. If we know the wiring, we know the outcome. Yet it also brings a subtle unease. If every thought and emotion is simply the product of blind mechanism, what becomes of personal agency, creativity, or meaning? Where, in that chain of electron flashes, is there room for the unpredictable sparkle of free will? Quantum consciousness, for all its scientific challenges, offers a different possibility. Quantum effects, by nature, are probabilistic and indeterminate. Measurement collapses a multitude of options into a single, unpredictable reality. If consciousness is rooted in the quantum world, then perhaps your own thoughts and choices are not perfectly mapped out from the start, but arise from a sea of possibilities, with your awareness helping to select a path at each moment. This softens determinism and opens a window, however small, for true novelty. Decisions born not just from previous causes, but from a deep process of reality making. The binding problem of consciousness, the way your senses, memories, and emotions are experienced as a seamless whole, also takes on new color in a quantum framework. If quantum coherence or even entanglement helps to intertwine the workings of the brain, it might explain why your awareness feels so unified. The possibility that consciousness is not simply divided up and processed in modules, but emerges when many parts resonate together, gives your own experience as a living, feeling person a deeper scientific resonance. Each moment of thought, each flash of memory, could be the graceful outcome of countless micro-events coming together in a quantum choreography within your cells. Quantum connections also reshape ancient questions about reality itself. Is the world out there truly separate from the observer, or is consciousness woven into the very process of what becomes real? Some interpretations of quantum mechanics, like the consciousness causes collapse view, suggest that awareness does not just observe the universe, but helps to co-create its manifest reality at each observation. In this vision, your experience, gentle, subjective, and ephemeral as it may sometimes seem, could hold more sway over the cosmos than you ever imagined. Practically, too, the exploration of quantum consciousness deepens our sense of wonder at the ordinary. Think of the microtubules that hold up your thoughts, the enzymes that fire your metabolism, the photons detected by your eyes. Even if the grandest quantum claims remain unproven, you are already a being who is inseparably entangled with the universe, built from atoms that once blazed in stars, participating each day in the grand, ancient cycles of birth and change. Belief in quantum mind ideas can influence how one approaches life's mysteries, fostering humility in the face of the unknown, appreciation for the limits of current knowledge, and curiosity about the potential for future discovery. It can also inspire a sense of belonging within the cosmos, to imagine that your own consciousness is, at least in some way, a local flowering of the universe's deepest patterns. For some, this brings comfort or awe. For others, skepticism, or a strengthened commitment to more classical explanations. In psychology and mental health, the language of connection, whether quantum or otherwise, reminds us that states of awareness can shift, bind, and heal in unexpected ways. The idea that the brain might harbor untapped quantum abilities, even if not yet proven, sometimes helps individuals imagine new possibilities for well-being or resilience. More concretely, research in quantum biology and neurophilosophy encourages interdisciplinary thinking, breaking down barriers between fields and sparking innovative therapies, technologies, and philosophies of mind. Ultimately, whether the hypothesis of quantum consciousness is true, partly true, or merely a poetic vision, it enriches the ancient human quest for self-knowledge. Your brain, after all, remains the seat of all you know, feel, and wonder. By asking whether it is tethered, even subtly, to the quantum cosmos, you participate in a legacy that stretches from ancient sages to the frontiers of modern physics. Whatever path science finds, every question asked in good faith, every attempt to reconcile personal experience with the grandeur of nature, brings you closer to understanding not just what you are made of, but what it might mean to be conscious, free, and deeply, quietly connected. As we near the restful end of our journey, let's softly survey the evolving horizon, the future of quantum consciousness research. Whether or not the most radical hypotheses prove correct, this is a field alive with curiosity, technical ingenuity, and a willingness to let big questions linger, a testament to the enduring human urge to understand the mind, not just as a collection of parts, but as a profound window onto reality itself. On the experimental front, scientists are crafting ever more sensitive tools to probe quantum effects in biology. Technologies such as ultrafast laser spectroscopy, femtosecond imaging, and quantum sensors are routinely used to measure vibrations, excitations, and fleeting coherence patterns in proteins and cellular structures. Each year, these instruments grow more refined, with higher resolution and greater ability to peer into the noisy, dynamic interiors of living cells, including neurons and even brain organoids, tiny clusters of human-derived brain tissue grown in the lab. Biophysicists are devising experiments to test whether microtubules can, under physiological conditions, support quantum coherence for biologically meaningful intervals. Novel approaches involve cooling brain samples to different temperatures, adjusting ion concentrations, or artificially shielding tubulin networks from external noise to look for changes in quantum signatures. Elsewhere, research on quantum tunneling in enzymes and sensory proteins expands our understanding of how quantum mechanics works across the broader spectrum of life. In neuroscience, new imaging strategies are mapping the brain's activity at ever smaller and faster scales. Scientists look for quantum-like oscillations, unexplained rhythms, flashes of biophotons, or anomalous correlations in network activity that might hint at non-classical information integration. Cutting-edge brain-computer interface projects, bolstered by artificial intelligence, help analyze these mountains of data for subtle signs of order that could reveal quantum underpinnings. While such research is still in its infancy, progress in adjacent fields offers quiet encouragement. On the theoretical side, researchers are developing more robust physical models for how quantum effects might be implemented, protected, and scaled up inside living systems. They are drawing upon the lessons of quantum computing, quantum error correction, and the intricacies of decoherence avoiding subspaces. Some pursue hybrid theories, blending quantum and classical models, suggesting that even partial quantum events might subtly influence the large-scale dynamics of the brain. The development of testable predictions is a focus, with theorists striving for hypotheses that can be precisely checked, repeated, and, if necessary, falsified by the wider scientific community. Interdisciplinary collaboration remains a hallmark of the field's promise. Physicists, neuroscientists, philosophers, chemists, engineers, and even mathematicians meet at conferences and virtual symposiums, sharing discoveries, demanding rigor, and cross-pollinating ideas. At the interface of quantum biology and neuroscience, new generations of graduate students are encouraged to think flexibly, practice careful skepticism, and follow evidence wherever it might lead, even if the findings are surprising, incremental, or in conflict with cherished beliefs. Looking ahead, the questions stretch as far as your imagination. Will experiments finally catch fleeting quantum coherence in the living brain? Could drugs, therapies, or technologies one day harness quantum properties for new kinds of healing or cognition? Might a quantum computer or an artificial neural system eventually reach a form of synthetic consciousness, not by copying the brain, but by echoing its quantum underpinnings? Or will the answers continue to reinforce the extraordinary sufficiency of classical network-based models, banishing quantum mind to the realm of scientific curiosity? Even as some await breakthrough evidence, others find value in the journey itself. The exploration of quantum consciousness shapes how we think about the relationship between mind and matter, between individual and cosmos, between the known and the inconceivable. For every experiment that fails to confirm quantum effects, fresh questions bloom about perception, agency, creativity, and what it means to be a thinking, sensing part of the universe. As night deepens and our journey slows, Remember that science itself is a great act of quiet attention, patiently returning to the unknown with new questions, new tools, and the ever-enduring belief that understanding, however partial or provisional, makes life richer and more deeply felt. Just as your own awareness arises from the seamless dance of brain and body, so the science of consciousness moves gently forward, guided by wonder, humility, and a longing to listen to the universe's most mysterious song. As our voyage through quantum consciousness draws to a close, let us settle softly into the present, where wonder, curiosity, and the gentle pull toward rest mingle in the hush of night. After trailing the enigmatic connections between brain and universe, tracing the sharp edges of skepticism and the soft light of discovery, it is time to let these ideas settle, not as final answers, but as nourishing questions, quietly accompanying you into sleep. Here, in the quiet space before dreams, the themes of our journey blend together. The pursuit of quantum consciousness has led us into the heart of scientific mystery. The search to explain how, from physical matter, emerges the immaterial reality of awareness. We have encountered microtubules, theorists daring enough to describe orchestrated quantum reductions, fierce debate over decoherence, and the robust creativity of alternative classical explanations. We have witnessed the astounding ingenuity of life. Birds sensing the pull of the planet's magnetic fields, plants harvesting sunlight with quantum grace, enzymes guiding life's chemistry with tunneling tricks, and always questions returning to the special wholeness of your own experience. What endures in all of this is a sense that your brain, while governed by the laws of matter, is always more than the sum of its parts. Every thought, memory, or moment of emotion marks the meeting of numberless tiny processes, classical, and maybe, just maybe, quantum. Whether or not quantum consciousness is borne out by future discoveries, the very act of wondering about it connects you, softly and deeply, to the unfolding of science and the inheritance of all who have wondered before. I'd still love to know where in the world you're watching from and what time it is there. Knowing that these explorations of mind and universe find their way into quiet rooms and tired hearts around the globe is a source of connection I treasure. One mind sharing with another across space, time, and scientific uncertainty. So as you nestle into comfort, let tonight's ideas cradle you. The possibility that your mind may resonate in some small way with the universe's deepest patterns. Know that pondering big questions is not a disturbance to sleep, but a gentle sedative for the soul, a way of reaffirming your place in the great unfolding mystery. May your dreams tonight echo the subtle music of quantum possibility. May rest come easily, as each neuron in your mind releases into stillness, and you become, if only for the span of sleep, an untroubled witness to the quiet but profound connection between consciousness and the cosmos. Good night, and may curiosity itself whisper you softly into dreams.